It is a pleasure to welcome you to second edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on design of foundations, which will be delivered by Emeritus Professor Harry Poulos. Emeritus Professor Harry Poulos is an Emeritus Professor at the University of Sydney, and also a Senior Consultant with Tetra Tech Coffee in Sydney, Australia. He has been involved in a large number of high-rise projects in Australia and overseas, including the Burj Khalifa in Dubai. He was the Australian Civil Engineer of the Year in 2003, and is a distinguished member of the American Society of Civil Engineers. In 2014, he was inducted into the U.S. National Academy of Engineering, and in 2020, he received the Peter Nicole Russell Medal from Engineers Australia for Lifetime Achievement in Engineering.
Good morning, or good afternoon, or good evening to all those who have hooked on to this presentation. And thank you very much to the organising committee for kindly inviting me to participate in this excellent series of lectures, and for indulging me in allowing me to divide my talk into two parts. So this evening, in my time, I'm going to talk firstly about the basics of foundation design and then focus on shallow foundations. And so I will start with an introduction, a background to the design process generally. I'll talk then about approaches to foundation design and the criteria for design. And then we'll look at shallow foundations, firstly, in terms of bearing capacity or the ultimate limit state. And then we'll look at settlement estimation or serviceability issues and look at sands and clays specifically. And then at the end, I'll say something fairly brief and fairly peripheral about foundations on expansive clay, because in many parts of the world, including Australia and India, we do have to cope with this type of situation. Now, from my viewpoint, the objective of these lectures is really to help people to understand some of the basic principles of foundation engineering and to raise awareness of the details involved. With the time we have available, I can't give you an in-depth exposition, and I've tried to sort of outline the philosophy here in the bottom part of this slide, because what I'm providing you with, I hope, is some relevant information. And it's up to you then to apply that information into knowledge, and then in due course, if this is what you want to do in your career, with experience, to convert that again into expertise. So all I'm doing is the first step of this journey towards expertise. Now, in this lecture, I'll assume that those involved are familiar with certain basics here. Firstly, the basic principles of soil mechanics, and in particular, the effective stress equation, which says that the effective stress is the total stress less the pore pressure, and the effective stress principle associated with that, which is that the strength of a soil and its behavior depends on effective stress, on that difference between total and pore pressure, total stress and pore pressure. I'm assuming then that people will also be familiar with the basic principles of mechanics and of equilibrium, and also that you will be familiar with the basics of elasticity, so we can convert stresses into strains or vice versa through elastic properties or pseudo-elastic properties of the soil or rock that we're dealing with. I've listed here 4 key references, which I think are worthwhile for people to consult. The book by Tomlinson, the book by Bowles. It's a very large book. It has a lot of material. Not all of it is up to date, but it generally is an excellent reference. A very good publication from Hong Kong, and also a state-of-the-art that I wrote with my colleagues, Professors Small and Carter, a few years ago, 20 years ago now, for the Istanbul conference. Now, in terms of how we, or what we need to consider for foundation design, these are the issues. Clearly, ultimate capacity is a primary issue. We must ensure that the foundation will not collapse. We then need to look at the settlement and the differential settlement and the tilt of the foundation and make sure that they allow the structure that they're supporting to be serviceable. And we also need to be able to look at how the foundation responds to lateral loads and moments, because in many cases, these will be important, particularly for tall buildings, and we have to be able to cope with those. Then, in many cases, we also need to look at dynamic behavior and earthquake response of the foundation and how that foundation affects the structure. And then from the viewpoint of structural design, we also need to be able to interact with our structural colleagues so that the foundation elements, the slab, the piles, if they're there, need to be designed structurally. And we also need to satisfy the requirements of durability, that in general, we need our structure to be durable over an extended period of time, typically 50 to 100 years. And finally, and I've got this as something that I think has been increasingly important, we need to be able to design foundations so that they're as sustainable as we can. And this involves trying to reduce our carbon footprint. And one of the ways of doing this is to try and design economically so that we limit the amount of concrete and steel that we use in our foundation systems. Now, there are, in my view, various stages of the design process. The first of these is a preliminary stage, and we do this to try and get an idea of what sort of requirements our foundation system will have, whether we're dealing with shallow or deep foundations, and it's the basis for developing the foundation concept. The second stage, once we've got into that, is a detail stage where we develop and optimize the design. And here we tend to interact very closely with the structural engineers, particularly if we're dealing with tall buildings. And then in the final stage, we make sure that we have the best and optimized solution that we can. Typically, we will check with alternative analyses to make sure that we haven't made any mistakes or overlooked any issues. And in many cases, particularly with large projects, we will have a peer review. And that is an extremely important part of the process, particularly for major projects. And I've got at the bottom just to note that the design tools that we use should be consistent with the stage of design. So for example, in the preliminary stage, we don't want to be using very advanced numerical analyses that take a long time and are expensive, simply because we generally don't have the final parameters. And in any case, we're just trying to get a ballpark idea of what our foundation system consists of. At the final stage, we need to pull out all our stops. We need to have the best parameters and the best possible analysis that is appropriate to our problem. Now, I found it convenient to categorize analysis and design methods into three categories. The first of these, and the simplest, is empirical methods, where we are based on prior experience and on simplified methods that have developed over the years with experience. Then I've got category 2 methods, which are soundly based, but they're simplified theory and or charts, so that they are part of the problem or the art of using this category is to simplify your real problem into something that we can analyze and idealize. And then finally, category 3 problems or methods are those where you use site-specific theory with various levels of sophistication of the soil model. So going through from simple, perhaps linear or plastic models in 3A through nonlinear models in 3B to advanced soil models in category 3C. And with the development of numerical methods over the past 3 or 4 decades, we now are able to, on occasion, where it's appropriate, even go to this level 3C analysis. Now, there are a number of factors that influence our selection of foundation type. Clearly, the location and type of structure, the ground conditions, the access for construction equipment, that is often very important because if we're in a congested urban area, there may be foundation options that we cannot use because construction equipment can't get there. Then we have the requirements of durability. We need to make sure that our construction doesn't adversely influence adjacent piles or foundations, adjacent structures or people, because there can be noise problems, for example, with driven piles. And of course, relative costs relate not only to economics, but also to sustainability. And finally, local construction practices that clearly, if we try and introduce a type of foundation which is totally unfamiliar in the location of the project, we may be asking for problems. Now, just very quickly, the foundation options that we have, obviously individual footings, whether they're shallow, square or rectangular footings, as I've shown here, or strip footings. They're very common for lightly loaded structures. Then if we go to somewhat heavier structures, we basically have a raft or a mat foundation. So the columns come onto the mat, and the mat helps to reduce any differential settlements that we might have between adjacent columns. And then we get into the deep foundations where we've got piles and pile groups. In this case, we've got a group of groups, but that's fine, where we're now largely transferring, excuse me, the loads through the upper, perhaps more compressible material to less compressible strata below. And then finally, one that has been increasingly used for tall buildings is the pile raft, where we have the raft actually bearing on the soil, but also supported by piles. And so that's a combined foundation system that has a number of advantages in terms of both cost and sustainability. Now, the first step that we have to recognize in design is characterizing the site. And this is an absolutely critical component of our design process. We need to understand the geology, and it helps if we have in our team engineering geologists that can tell us how the site geology evolved. We need to understand the stratigraphy, so we would do various types of boring and in situ testing. And then we need to quantify the relevant geotechnical parameters. And that's usually done, excuse me, on the basis of in situ testing or laboratory testing or load testing or a combination of all three, ideally a combination of all three. Now, it is critical, as I mentioned before, because ground conditions tend to be the greatest source of uncertainty in many projects. And so we need to understand the history of the site, because that may give us clues on the behavior of the deposits. And we also need to understand the recent history of the site, because just because we've come onto the site for our project does not mean that time zero starts from when we walk onto the site. There may be ongoing processes. The site may have been subjected to filling or reclamation some years ago, and that may still be happening, that the consolidation due to that previous process may still be happening. We also need to be aware that there may be changes in the ground conditions between when we do the site investigation and when we undertake the construction. And I'm sure all of you who are geotechnical engineers will know and appreciate that economizing on this phase of the project is illogical and potentially dangerous. And this is just a diagram from Clayton from some years ago, showing on the vertical axis the potential cost overrun as a percentage of the initial cost versus the relative cost of the site investigation as a percentage of the overall cost. And although there's a lot of scatter here, you can see that as an upper bound, the more we can spend on site investigation, the less likely it is that we will have a significant cost overrun. So site investigation is not really a cost, it's an investment in reducing your risks. And that's a message that we need to emphasize to our clients. In terms of the ground investigation itself, how far do we need to go? Ideally, according to Tomlinson, we need to go to at least 1.5 breadths below the sort of level of the foundations. We need to be able to prove rock for a decent distance below the top of the rock. And we need to make sure in particular that we don't stop just because we may hit rock. We say, well, the rest of it is all rock. It may not be, because there are some circumstances where there are compressible layers below stiffer layers that exist. So you need to be very careful with those sort of situations. So that's all I can say now on that very critical issue. Coming now to the actual approaches for design. In the traditional method of design, where we design for safety, we used to have an overall safety factor such that our working load is equal to the ultimate load capacity divided by some factor of safety, typically somewhere between 2 and 3 plus. And that, I think, has ruled foundation design for many decades, up until probably the last 2 or 3 decades. In recent years, the Europeans have come up with partial safety factors. So they've factored up the loads to allow for uncertainties in the loads and factored down the soil parameters, that is the strength parameters, to compute the design resistance. There is another approach which we use here in Australia, and I think now is becoming increasingly used around the world, and that's what is known as the load and resistance factor design approach. And what we do here is that we factor up the loads by load factors, and we factor down our calculated ultimate capacities of the foundation, the shaft and the base of their piles, and we try and make sure that the factored down resistance is equal to or greater than the factored up loads. And so that's an approach that we use for pile and foundation design in Australia and many other cases. There is also an approach that is not, to be honest, much used in foundation design, although it's increasingly used, I think, in geotechnical earthquake engineering, and that's the probabilistic approach, where we try and make sure that with our quantitative evaluation of the probability of failure, that is less than some specified allowable value, typically 10 to the minus 4, 1 in 10,000 risk per annum. So they're the ultimate limit state criteria, and the factor down resistance, certainly in my country here, we factor down the calculated ultimate capacity by what we call the geotechnical reduction factor. And our standard for piling has a process that looks at factors including the site conditions, the uncertainties involved there, the type of structure and foundation, and the consequences of failure. And typically that reduction factor varies from about 0.4, which is the most conservative design, to around about 0.8, which is the most bold design. In terms of serviceability, we need to specify allowable settlements and differential settlements, possibly lateral movements, and these depend on the nature of the structure and the ground conditions. And as I mentioned earlier, durability increasingly, and particularly for structures that support marine facilities, we need to make sure that we have durability over an extended period of time. In terms of design loads, these are generally specified in the loading standards. We generally are provided with ultimate limit state loads. These are for failure assessment and also for serviceability loads. There are various components of load, which I've listed here. And in general, we rely on our structural colleagues to provide us with those sorts of numbers so that we can then start our foundation assessment from a geotechnical viewpoint. In terms of the load capacity, what we have to do, this is where we start getting serious here, we need to make an estimate of the ultimate load capacity of the foundation system, and that needs to include all the likely loads that will act on the foundation. And in general, there are 6 components of loads. There's vertical, there's 2 horizontal components, 2 moment components, and possibly torsion. And so ideally, our methods of design should be able to look at all of those load combinations. Now, coming on to how we assess load capacity, there are a number of common methods that are essentially empirical. So these would be, in my categorization, category 1 methods based on experience, and methods that use such parameters as the standard penetration test, the cone penetration test, or the pressure meter test. Then if we look at category 2 methods, we have limit equilibrium methods, perhaps the method of slices, for example, and the theory of plasticity. And particularly the theory of plasticity, it is soundly based, but quite simplified, because generally we can only handle single or double layers. And then finally, we have the category 3 methods, such as finite element methods, where we look at using advanced numerical procedures. In terms of the settlement and movement assessment, that may well control the foundation design. Certainly in many tall building cases, it's not so much the ultimate capacity, but the settlement and differential settlement that actually is the controlling factor. And there may also be certain structures where lateral movements are important. For example, bridge foundations or radar trackers or communication towers where you need a high degree of stability of the structure. So the issue of serviceability is really of critical importance, and it's been increasingly recognized as being important. Once upon a time, you just did a factor of safety 3 calculation, and that was your foundation design. Now we have to be much more specific about serviceability. Now, coming on to serviceability, we have to recognize that there are various components of settlement and movement that we may need to consider. The first of these is immediate settlement or movement, which occurs as soon as the loads are applied to the foundation, and they are generally movements that are due to shear deformations within the ground. The second component is consolidation or movement, and these occur because the loading of the soil causes excess pore pressures in the soil, and you get a gradual dissipation of those excess pore pressures as the water manages to escape, and you get a change in volume. So you get a settlement, which is time dependent, and that the amount of settlement depends on the stiffness of the ground. The rate at which that settlement develops depends largely on the soil permeability and on the geometry of the soil profile. So the rate of settlement and the rate of movement, as well as its magnitude, can be important. And these are things that we must assess. In addition to those, and these are fairly well recognized, the immediate and consolidation settlements, we have another component of creep or secondary consolidation, which tends to occur at more or less constant effective stress. It's a long-term phenomenon, and I think arises from changes in soil structure with time and the structural viscosity of the soil skeleton. And finally, if we have a situation where we have repeated loading, particularly if we're dealing with sands and granular materials, then there may be a gradual racketing down of the foundation system. Now, that's not something I'm going to consider in detail here, but let's be aware that where we have storage facilities, oil tanks that are loaded and unloaded, there may be a consequent time-dependent movement due to that repetitive loading. In terms of the settlement criteria, the allowable settlement depends, as we said before, on the type of structure, its height, its rigidity, the function and location, and how quickly that settlement develops, and the presence of sensitive equipment or processes in the structure. For example, we've had to design foundations for printing presses, and there you have a very limited tolerance to movements and differential movements, so that you have very stringent requirements for settlement and differential settlement under those circumstances. So it is important that we distinguish between the total settlement, which can cause damage to the surfaces of the structure, differential settlement, which may be very noticeable in high buildings, and also differential settlement within the structure itself, which can lead to structural damage and also damage of the foundation. In terms of allowable settlements, many years ago, there were some suggestions made by Skempton and MacDonald about allowable foundations, allowable settlement of shallow foundations. And typically, those allowable settlements were somewhat greater in clay than on sand, simply because in clay, the settlements tend to develop slowly with time, and so a structure can adjust more gradually to those settlements than if the situation is with sand, where there the settlements tend to be very rapid, responding to the load. And so we had 65 or 40 millimeters for isolated foundations, and with rafts, somewhat greater settlements. Now, in recent years, where we've had to be designing buildings that are hundreds of meters tall, it's very difficult to limit settlements to these sorts of values. And so we've had to expand our allowable settlements to 100 to 120 millimeters. We have buildings in Frankfurt in Germany that have settled in excess of 120 millimeters and are performing just fine. So it is possible to have greater settlements than the ones that we used to be limited to. In terms of angular distortions, I've just got, there's quite a bit of literature on this, but there's probably three important numbers. If you have an angular distortion of in excess of 1 in 150, so that's quite a distortion, then you're likely to get structural damage. If you've got a distortion worse than 1 in 300, you may get architectural damage, you may get cracking of walls and so on. And a common criterion that we tend to work with many buildings is that we try and limit the angular distortion to 1 in 500. And if we can do that generally with most buildings, except architecturally sensitive buildings, that's pretty much adequate. One important recognition, I think, over the past couple of decades is that not only is the angular distortion itself important in terms of the vertical movements, but if we have horizontal strain, then the presence of horizontal strain can make the potential for damage worse. And this is a diagram that was developed by Professor Berlin and his colleagues. It shows on the vertical axis that the deflection ratio, so that's the delta on L, if you like, so minus 0.1%, so that's 1 in 1,000, 1 in 500, 1 in 300. And these are different categories of damage going from very little, 0, to very severe. And you see if a particular angular distortion is associated with a large horizontal strain, then the level of damage that you may expect is really quite large. So one of the lessons of this is that if we can tie our foundation system together and limit the amount of horizontal strain it experiences, then the risks of getting significant damage are reduced. Now, before I go into the actual design methods, we need to understand that design methods that we use are inevitably limited in some way. They have limitations. All of them involve uncertainty and risk, regardless of the level of sophistication. And I have to say that highly sophisticated methods are in themselves liable to risk simply because some of them involve parameters that we're not really familiar with or that haven't been well understood or quantified. We tend to perhaps accept default values that may not be relevant. And the other thing that I feel very strongly about, and if there's one message that I leave you with, it's this, that if you are using sophisticated methods, please check them against simpler alternative methods to make sure that you're getting a sensible answer. Because if somebody comes up to you and says, I've done a calculation and we have 10 kilopascals and it's going to settle 2 meters, I think you would have to question whether that calculation is valid, because it doesn't fit with simple methods and it doesn't fit with experience. So the key risk factors then that we need to recognize: inappropriate characterization of the ground. If you have a stupid ground model, no matter how great your design method is, you will not get good results. If you have poorly chosen geotechnical parameters, that's a big risk. You have uncertainties inevitably in the design loads and in the design tools. And importantly, and this is not so much with conventional buildings, but with some more exotic structures, there may be unanticipated mechanisms of behavior that you don't account for. And these can also be risks. So let's now move on to the actual design calculations that we have to do for shallow foundations. So I'm going to talk about bearing capacity first in terms of simple methods, category 1, and theoretical methods. Then I'll talk about shallow foundations on clay and then on sand. And I'll say something about expansive soils. And right at the end, I'll just show you some of the potential for using category 3 methods to help us to both quantify various characteristics and also to understand behavior of the foundation system better. This is what we want to avoid. This is a very classic failure, the Transcona grain elevators in Canada more than a century ago. Basically, the load in these grain elevators was more than could be sustained by the ground, which was a clay. And so you had this classic rotational failure. And in fact, there's been some papers written about this that demonstrate that our theories, when properly applied, would have predicted this failure. And I believe that those elevators were subsequently reinstated and are functioning. Now, coming then on to how do we work out what the ultimate bearing capacity of a particular situation is? Well, category 1 methods, this is an example of my friend Luciano de Cor from Brazil, who came up with a series of correlations of the ultimate bearing capacity being related to the SPT value corrected for energy at a depth of about half of the minimum footing width. And that, what he said was that the ultimate bearing capacity, depending on whether you have sands or clays, is somewhere between 90 and 65 times the N value in kilopascals. Now that's a delightfully simple first approach that gives you, if you've got an SPT of 10 and you've got sands, then your ultimate bearing capacity is 900 kPa. And that's just your first ballpark figure on the bearing capacity. There are also correlations with the cone penetration test, and again, they're very simple. One of them that is used is that the ultimate bearing capacity is a quarter of the average cone resistance within the zone of influence of your footing. And so, again, with very little calculation, but with a proper ground characterization, you can get a reasonable first indication of what the bearing capacity should be. Now, of course, we generally need to go a bit further than that, and we have available to us category 2 methods, which are generally based on some form of limit equilibrium or plasticity theory. Now, this is a generalized theory where the ultimate bearing capacity has 3 components: a component due to soil cohesion, a component due to the size of the footing, and a component due to the embedment or the overburden pressure of the footing. And these are various factors that allow us to consider the shape, the inclination of the footing, the depth, the slope of the surface, and the slope of the base of the footing. There's also a factor for compressibility, which I'll show you can be important for loose sands. And these bearing capacity factors, NC, N gamma, and NQ, well recognized, depend on the friction angle of the soil. Here are some solutions showing those 3 methods. They were modified from Terzaghi's original theory, but they are plotted against the friction angle, and the higher the friction angle, the bigger is the theoretical bearing capacity factor. And so the denser the sand, for example, the higher the friction angle, the higher the bearing capacity. That's what you would expect. And there are also correction factors for load, inclination, and eccentricity. And for example, for eccentricity, one of the simple things we do, and surprisingly, we've checked it out with more sophisticated analysis, and it works out quite well. If you've got bending moments in 2 directions so that you have a vertical load that effectively has eccentricity in both directions, you can handle that by looking at a reduced area where the vertical load is at the centroid of that reduced area. And by just taking that reduced area as your vertically loaded area, you can get an indication of the bearing capacity of the eccentrically loaded foundation. Now, I mentioned soil compressibility before, and this is something that I think we started to recognize. It was a very interesting problem that we had some 40 years ago now in Bass Strait, where an offshore platform was being constructed, and it was clear that it was on calcareous sand, and the calcareous sand, even though it appeared to have a high friction angle, had a bearing capacity that was substantially lower than we would have expected from a silica sand. There was quite a lot of research done, and this is, for example, a load versus settlement relationship from model tests for silica sand and for calcareous sand. Both of those had friction angles which were fairly similar. In fact, if I remember correctly, the calcareous sand friction angle was over 40, the silica sand was about 36, 38, and yet the bearing capacity of the calcareous sand was significantly less than that of the silica sand. And it turned out that the compressibility of that calcareous sand was much greater than the silica sand, and that influenced the bearing capacity. And just as a matter of fact, it turned out that if you use Terzaghi's theory with a reduced friction angle, the one that he suggested for local shear, then you got much closer to the actual bearing capacity that was measured. So that's something, and again, you have to bear in mind that it isn't just the friction angle of a sand that is important, it is also how compressible it is. Now, very importantly, we need to recognize that soil being a somewhat complex material, the parameters of that soil depend on how the soil is loaded. And so in geotechnical practice, we look at generally two sets of parameters at least. The short-term parameters, which is relevant for rapid or undrained loading on clay soils. Here we use total stresses, and we have total stress parameters, Cu, undrained shear strength, and Φu, undrained friction angle. And for saturated clays, that undrained friction angle tends to be 0. And then if we're dealing with long-term capacity, where the loads have been on for a long period of time, so that tends to be for long-term situations in clays or for sands generally. Now we need to use effective stress parameters C' and Φ'. These are effective stress cohesion and friction angle with effective stresses. And here now, the location of the water table or the distribution of pore pressure can be important and critical. Now, ideally, as geotechnical engineers, we should be looking at both cases. The short-term case, particularly for foundations on clay, looking at how critical that bearing capacity is when we quickly load it, and then what that bearing capacity is if the load stays on for a long time. And in general, it turns out that in clays, the undrained bearing capacity tends to be critical. The long-term capacity tends to be greater simply because the soil consolidates and gets stiffer under the action of the load that is sustained over a period of time. Just be careful, however, that this is not a universal rule. If you have a situation such as you have with excavations, where you have a reduction in stress over time in a clay, so that when you excavate a clay, you're actually reducing the stresses in the clay. In the long term, that will reduce the effective stresses in the clay and reduce the strength. And so if you're doing such a problem with excavations, you must look both at short-term capacity and at long-term capacity. And it's possible that the long-term situation may be critical under those unloading or excavation conditions. There are some special cases, particularly for clay soils that people have looked at, such as where you have varying cohesion with depth, fissured clays, footings near a slope, and two-layer profiles. Let me just very briefly show these to you without any great explanation. These are solutions that my late colleagues Davis and Booker obtained many years ago, where you can calculate the bearing capacity of a foundation where the shear strength is increasing with depth. And in general, what you find is, of course, that because the soil is getting stronger with depth, the bearing capacity will tend to be greater than if it was just a constant strength with depth. And there's also situations which are quite realistic in many cases, particularly for embankments on soft clay, where you have a crust or a desiccated upper layer, and then you have a normally consolidated clay below. And so this is, again, a case that Davis and Booker examined. And then you have two-layer situations. It's hard to be very general about these, but there's been some work done that provide this sort of approximation of a modified bearing capacity factor when you've got a two-layer system here. In general, when we're dealing with shallow foundations on clay, the bearing capacity undrained is somewhere between 5 and 6 times the undrained shear strength of the clay. And so that's always the first sort of point of reference. And then if you've got stiffer clay underneath, then it'll be a bit more. If you've got softer clay underneath, you need to be very careful about that. So let me now move on to the issue of how we estimate the settlement of foundations on clay. And we have a number of methods here. I won't have time to go into all of these, but we start off with the traditional one-dimensional method, which was the original Terzaghi method developed back almost a century ago. And that says that the settlement process is one-dimensional, so that when we put a vertical load on, we will get a vertical settlement, and that will be as a consequence of the consolidation of the clay. And so that is the only component of settlement we have. Subsequent to that, in subsequent decades, it was recognized that you also had the potential for an immediate settlement in clay due to shear deformations. And so there were various modifications. Then in the 60s, there were methods that used elasticity, and I'll mention those in a little more detail in a minute. And then, of course, in recent years, we've had the use of elastic and nonlinear finite element methods for estimating settlements. So just looking at a couple of those, the traditional method developed by Terzaghi is a one-dimensional method, assuming that the settlement arises from consolidation due to the increase in effective stress and the dissipation of excess pore pressures. And so this is one expression that the settlement is an integration of a coefficient of volume decrease times the increase in final vertical effective stress integrated over the layers. There are, of course, other forms of that expression using, for example, compression index. Now, there are limitations to that approach because we know that there are, in addition to vertical strains, there are also horizontal strains and shear strains. And also, we recognize that not only can pore water pressures dissipate vertically, but they can also, in general, dissipate horizontally. So if we've got a problem like this, where we've got a relatively shallow layer of clay and a wide loading, then one-dimensional is pretty good for that. But if we've got a relatively limited footing size on a deeper layer, that may tend to underpredict. Now, in fact, we can look at this theoretically, and what I've got here is the ratio of the one-dimensional to the three-dimensional settlement on the vertical axis. And here we've got the relative depth of the clay layer to the radius of the footing. There are two cases, constant modulus and increasing modulus with depth. But just to cut a long story short, the important thing is that these are different values of the drain-Poisson's ratio. In general, most well-behaved soils have Poisson's ratios that are 0.3 or thereabouts. And so the long and the short of this is that if you have a normal soil, even if you have a reasonably deep layer, your underestimate of settlement with the one-dimensional process will tend to be no worse than about 20%. And that's not too bad in terms of geotechnical terms for a simple calculation. The only time you may get worse than that is if you've got a peculiar soil which has a very high Poisson's ratio effective and a very deep layer where your errors may be somewhat greater. Now, I mentioned the use of three-dimensional elasticity, and this is a more versatile approach because a foundation does cause three-dimensional strains. The soil goes down, but it also goes out. And it also allows you to estimate the immediate settlement due to shear. It also allows you to estimate the effects of lateral as well as vertical drainage. Now, there are 2 or 3 ways of incorporating elasticity. The simplest approach, and this is, again, what I'd call a category 2 approach, and one that you can get a very quick order of magnitude answer. You can use elastic displacement theory, and there's been a number of solutions presented. This is one of them. And this says that the settlement are 2 factors, mu0, mu1, times the pressure on the footing times the width of the footing divided by Young's modulus of the soil. And those 2 parameters depend on the embedment depth and also on the thickness of the layer relative to the width of the footing, and also on the length to breadth of the footing. So that's about, at worst, once you've got a modulus, that's about a 2 or 3 minute calculation to calculate a settlement. And so that really is an excellent way of doing a preliminary calculation, and also a check calculation for your more complex analysis methods. Here's another set of theoretical solutions. In this case, settlement is the average pressure times the radius of the circular footing times an influence factor divided by modulus, where the influence factor here depends on Poisson's ratio and also on the relative thickness of the soil layer. And another approach, which is really, it's just a more detailed approach, is that you can use the calculated stresses within the soil mass due to the loading, together with Poisson's ratio and modulus of the soil, to calculate the settlement by integrating the strains over the layer thickness. The stresses we often get from Boussinesq's equations, and the strains from elastic theory. Here are some more detailed distributions of a vertical strain with depth below the circular footing. So you can use those and calculate the strains at different levels and sum those up to get a settlement. Now, very importantly, when you're using elastic theory, again, it's important that you recognize that there are at least 2 values of modulus or sets of moduli that you can use. The first of these is undrained modulus for foundations on clay. This is how the soil reacts to rapid or undrained loading. And that gives you an undrained modulus and a Poisson's ratio, which in a saturated soil is 0.5. So if you use those values in your elastic theory, you will get an immediate settlement. That is the settlement that you would expect as soon as the load is applied to your footing. Now, the other set of parameters are the long-term parameters. These are E' and U', and these are the stiffness and Poisson's ratio of the soil after the pore pressures have dissipated and after the settlement process is finished. And that gives you the total final settlement. And the consolidation settlement then is the difference between the total settlement and the immediate settlement. Now, theoretically, there is a relationship between the undrained and drained modulus values, which is here, but in reality, that holds only for stiff soils that behave more or less elastically. Now, if we take account of the fact that the consolidation settlement takes time to develop, then we introduce a degree of settlement, UT, so that the settlement at any time is the immediate settlement plus this degree of settlement times the final consolidation settlement, which is calculated as the difference between the total settlement and the immediate settlement. And so our next challenge will be to get that degree of settlement. Before we go on to that, we also need to recognize that in our elastic theory, we don't have allowance for the fact that the soil may actually yield in parts. And there is what we call a local yield in the soil, particularly as the factor of safety decreases or the stress level increases. And so we've come up with a correction to the immediate settlement to allow for local yield, and that is a function of the applied stress ratio, which is in effect 1 on the factor of safety, and the initial stress ratio. So the corrected immediate settlement is the value from elastic theory divided by a correction factor, which is less than or equal to 1. So in other words, the immediate settlement will be equal to or greater than the elastic immediate settlement. And these are the local yield factors. That's the correction for the local yield. This is the applied stress ratio, and this is the initial stress ratio. The closer you are to non-uniform horizontal and vertical stresses, the less likely it is that local yield will be important. But if you have low factors of safety, and that can happen, of course, with embankments on soft clay, then this local yield effect can be fairly important. Just now getting on to how we get those parameters, the E' and U'. One of the earlier methods was through stress path triaxial testing. And the whole principle, I won't try and describe this in great detail, but the principle of this method of testing, and it was one that was also developed almost contemporaneously by Professor Lamb at MIT, you try and subject the soil sample in the lab to the same stress history as that anticipated in the ground. So you take your soil sample, you try and return it to its native stress conditions in the ground, and then you apply vertical and horizontal stress increments to the soil sample, firstly under undrained conditions to see how that soil would respond to rapid changes in stress. Then you open the drainage and you allow drainage to occur, and that will allow you to calculate what the long-term stiffness and Poisson's ratio is of the soil. So that has been used fairly extensively, but I guess I have to say, as time goes on, people tend to use less of this sophisticated laboratory testing and more of in situ testing. And then if we look at what then we have available in terms of in situ testing, one of the important developments, I believe, over the past couple of decades has been the use of small strain modulus values for estimating, firstly, the small strain shear modulus, because there is a direct correlation between the small strain shear modulus, GI, and the shear wave velocity, VS, that you can measure either with geophysical methods or with methods such as seismic cones. And rho here is the mass density of the soil. And you can get that small strain shear modulus. We often do geophysics these days, so we get shear wave velocity, and that enables us to get a small strain shear modulus. And what we've found just in practice is that if we reduce that small strain modulus by a factor of about 0.2, so we take 1/5 of that value, then we get a value that is quite reasonable in terms of preliminary serviceability assessments. And I just point this out. This is work that was done by Professor Paul Main and others, Fahy and Carter in particular, looking at how the modulus degrades with stress level. And typically, if we've got stress levels in the order of 0.4 to 0.5, in other words, factors of safety, somewhere in the region of 2 to 2.5, then you see that that reduction factor is around about 0.2, which is what we find. And finally, just to indicate to you without going into detail, it is possible to also then relate both the drained and the undrained modulus to that small strain shear modulus and the shear stress level for different compressibilities of the soil as measured by the compression ratio. Again, I don't have time to go into that, but just be aware that this small strain shear modulus, which we can get really as part of a routine, good contemporary site investigation, we can use quantitatively very productively now for settlement estimates. In terms of rate of settlement, the original theory that Terzaghi developed, very widely used still, is only for vertical drainage. But we can modify that to allow for three-dimensional effects. The fact that the soil pore pressures can drain laterally as well as vertically. And there are now solutions that enable us to look at that. Here is one of those sort of solutions. This was really some time back that we developed this. This is a degree of consolidation. This is a dimensionless time factor. This is the one-dimensional theoretical solution that Terzaghi obtained, and this is for a layer of clay subjected to a circular loading. And if you've got truly one-dimensional conditions, that's how the soil would consolidate with time from 0 to 100% over a fairly wide time period. Now, if you have a soil layer that is relatively deep, then the time taken to reach a particular degree of consolidation can be far, far less. So even if you've got a layer that's 5 times the thickness is 5 times the radius, then the soil can, in this case, consolidates about, in this case, maybe 10 times more rapidly. And so three-dimensional consolidation is important because it accelerates the rate of consolidation, which is often a benefit to us. In terms of creep and secondary consolidation, this is a complication, but it's something that we need to recognize. And the creep is generally characterized by a linear relationship between the settlement and the logarithm of time. And we developed this C alpha parameter, which is the change of void ratio per log cycle of time. Now, work that Mesri and his colleagues did was very important because it recognized and demonstrated that this C alpha is related to the compression index of the soil, a primary compression, typically somewhere between 0.02 and 0.06 times the compression index, but around about 0.04 on average. And so if we've got the compression index, we get a first estimate of the secondary compression index. The major problem, of course, is when does that creep start? And it's convenient really to add the creep settlement to the conventional consolidation settlement, either at a predetermined time or at a predetermined degree of consolidation, for example, 90–95%, or when the gradient of the primary consolidation curve is equal to the rate of creep. There's no real fixed, well-established approach on this. It's something that I guess everybody has to do to satisfy themselves. Coming on to sands, settlement of footings on sand, there's a remarkable number of methods available, and they range from purely empirical methods to nonlinear finite element methods. But a lot of these are what we might call category 1 methods, relying on SPT or CPT data. And a lot of them have made use of case histories. Now, I've said that consistent success in obtaining accurate predictions remains elusive, and I'll show you that in a minute. Here's a listing, and again, I won't go through these, of various methods of estimating settlements of foundations on sand. Many of these are based on SPTs. A lot of these are from the earlier days of our profession. Some of the more refined methods use CPT, particularly Schmertmann. and then others use various other parameters or refinements. This is one of those methods, Berland and Burbridge, which are basically, they're based on empirical methods which relate the settlement per unit applied pressure. So it's almost like a modulus associated reaction inverted against footing breadth as a function of the relative density of the sand. You see there's a huge spread of results, bearing in mind that this is a log scale. And so immediately you have to recognize that using this sort of empirical correlation is unlikely to get you really accurate results, but it may give you a first indication. I just mentioned here Schmertmann's method because it turns out this is, I think, a fairly widely used method, particularly when you've got cone resistance data. Schmertmann uses, in effect, a simplified strain integration method that he uses these simplified distributions of strain, that's the influence factor versus relative depth, and he integrates the strains using a modulus either of twice the cone resistance at any depth if you've got circular footings, or 3.5 times the cone resistance if you've got strip footings. And you've got a couple of modification factors for stress level and also for time, because there is a time effect generally with settlement of footings on sand. So that's Schmertmann's method. Now, Tan and Duncan some years back did an assessment of the accuracy of various methods when applied to certain problems. And on the vertical axis, they have a measure of reliability, and on the horizontal axis, they have the average calculated on measured settlement. So if you had a method that was perfect, but it gave you an average calculated settlement that was equal to the measured settlement and 100% reliable, you'd be up here. What you see is that a lot of our methods are not that reliable, and the vast majority of methods that are in common use tend to have the calculated method greater than the measured settlement. Okay, so we tend to be conservative, which is not that terrible, but it can be really expensive and now perhaps not in the best interests of sustainability. Now, there was an interesting case study some years back by Briot and Gibbons, where they did a series of reasonably large shallow footing tests on a test site at Texas A&M University. It was essentially sand, and they were SPTs and CPTs and cones and pressure meter tests. And a number of people were asked to make predictions of the settlement of these footings. And I was foolish enough to be one of those that undertook a prediction. And there were various, these are not particularly from any one person, but these are a series for one of the footings of the predictions of settlement with different methods. 39 mil, 28 Schmertmann, 21 Berland and Burbridge, elasticity 18, elasticity using pressure meter, stress dependent modulus, which was my prediction, 32. The most sophisticated analysis used a three-dimensional finite element method with a constitutive saw model and got 75 millimeters, and the measured was 14. So everybody over-predicted, and the most sophisticated method gave the biggest over-prediction. So I guess this just reinforces the caution that I set out before, that just because you use a very sophisticated method does not necessarily mean that you will get a better prediction. Much of the level of success that you have depends on how you quantify the ground and what parameters you assign to it. So as far as that's concerned, most methods tend to overestimate settlements. Simple elasticity methods are not that bad. Sophisticated analysis doesn't necessarily improve our ability to predict. And the key really lies in terms of the soil modulus rather than the method. Now, just finally, just a few slides on expansive clay problems. Our design strategies, when we have expansive clays, the problem is this, that the soil tends to be sensitive to changes in moisture content. If the soil increases in moisture content, you tend to get a swelling of the soil. If you get a drying out of the soil, then it tends to shrink. Now, you have certain strategies. You can try and control the moisture so that you isolate the soil from moisture changes. Well, you can try and stabilize it, or you can try and isolate the superstructure from soil movements, or you design a stiff foundation that can resist the differential settlements. And this is just an illustration of the sort of things that can happen. This is particularly important for lightly loaded structures in domestic situations, particularly with your foundations near the edge of a building. If you have no protection or no means of controlling the moisture, then the ground tends to go up and down, and that will react on the soil, and your structure can be shoved up and down accordingly and get differential settlements and structural damage. You can control moisture with drains so that you try and stop that. You can have horizontal barriers and vertical barriers. If you can even put a horizontal impermeable layer on the soil near the structure, then that tends to reduce the potential for change of moisture content. You can try stabilizing the soil with various methods, or if it's really important, you can remove and replace the expansive soil with something that is relatively inert, or you can try pre-wetting the soil before you isolate it moisture-wise. As far as foundations are concerned, you can look at a stiffened slab on grade or a monolithic wall and slab. You can have modified perimeter footings, wall and basement construction, or drill pier and beam. This is a form of construction that's reasonably widely used here in Australia for construction, particularly in cities like Adelaide, which have a lot of expansive soils. And you have a mat which is reinforced with strips and beams, so-called waffle pod, so that that stiffens up the slab and makes it stiffer against ground movements. And you need in the design to define the heave and the loading. You assume beam spacing and configuration. You need to work out the bending moments, and you need to have a structural analysis so that you make sure that it is both structurally and geotechnically adequate. Here's a pier and beam solution that you now have your structure either on a bell pier or on a straight pier, and here you may have a slab and a wall which is supported on that sort of system. And I'll say a little bit more about piers and expansive soils tomorrow. Here, the pier length is based on the depth of seasonal moisture fluctuations. Ideally, we need to take it below that reactive zone. The diameter tends to be based on the minimum dead load. You need to reinforce the pier to resist tension, and you need to have a grade beam which can resist the floor and wall loads. And finally, we just need to recognize that these days we have a formidable array of methods of computer analysis that are available to us. I've listed here 4 commercially available programs: the 2D and 3D Plaxis and the 2D and 3D FLAC programs. Plaxis, of course, is finite element. FLAC is finite difference. And they are extremely versatile. And really the key challenge here is to develop an appropriate soil model and get the right sort of parameters. Now, I'm not, again, going to go into detail on that, what I did want to show you was some of the interesting things that these sorts of analyses can do for us, not always necessarily project specific, but getting us also to understand how foundations and soils behave. So this is an analysis that was done by my colleagues, John Small and John Carter. And here is a foundation that I think it's on clay, where the friction angle of the clay is 20 degrees, and the load was put on slowly. Consolidation is allowed to occur as the load goes on. And so we find that under that system of slow loading with the dissipation of pore pressures, this is how the foundation tends to move towards failure. You'll see we have the well-established sort of cone under the footing. This is, of course, the axis of symmetry on the left-hand side. So you have a cone that goes down, and then you have a sort of, not quite a slip circle, but something similar to a slip circle going up. And so that's the mechanism of behavior. This is the load settlement behavior up to failure. So as we apply the load very slowly, we get an increase in settlement until we get drain failure. And in this case, drain failure is at a pressure of about 290 kilopascals. Okay, that's the collapse load. Now, if we look at the same problem, but now we load the clay very rapidly so that we allow no dissipation of pore pressures, the load comes on very rapidly. Now we have a different mode. If you were to compare the two, which I haven't done, you'll see that this cone is a bit bigger. This is a sort of shallower circle. It moves up more. And the interesting thing is that here is the load settlement behavior, that now we have a stiffer response, which is because the initial settlement, of course, is less than the total settlement. But you see that we get an ultimate load pressure, which is 100 kilopascals, which is almost a third of the bearing capacity long term. And so this, I guess, just verifies what we had known from basic bearing capacity theory, that under these sort of conditions, under loading conditions where we have rapid loading, the rapid loading case will be the critical case, and the long-term case, if we can put the load on very slowly and allow dissipation to occur, then the loads that we can sustain are going to be significantly greater than those which we could sustain with very rapid loading. So that, ladies and gentlemen, is the end of this presentation. I've put a lot of material out there. I haven't had the opportunity to really discuss it in great detail, but hopefully what you may have gained from this is some broad indication of some of the methods we have, particularly some of the category 1 and 2 methods that we use and use very widely in initial design and also in fairly routine design. And also, perhaps you've seen some of the potential of what our category 3 methods are able to do. So I'll stop at that stage, and if there are any questions, I'll do my best to answer them.
This first question comes from Dr. Goh from Indonesia. He just asked, what's your opinion on the current situation of Millennium Tower in San Francisco? That some people believe that the dewatering of the adjacent subway and basement excavation might have aggravated the settlement problem. However, if that was the case, how come the settlement was only tilted towards one corner of the building itself? Was the proposed solution of installing perimeter contiguous piles was appropriate?
That's a very vexed question. I am not fully familiar with the case. All I can say is that if there was dewatering, and I think there was dewatering in a number of locations around the Millennium Tower. In principle, it would have had the potential to increase the settlement of the building. As I understand it, the building had already settled prior to the dewatering processes, so it probably didn't help the process in any way. It may have contributed somewhat, but how much, I think, is a matter that I think is still under debate. It is under litigation, and so I can't really add anything more to it than that. Whether the underpinning was an appropriate solution, generally, in principle, if you have a foundation system that isn't functioning, and if you have the ability to correct it, then it's always a good idea to try and do so. Having said that, you must always be careful that in the process of installing the corrective measures, you don't actually exacerbate the problem, because inevitably, particularly under a highly loaded 58-story building, you'll have a high stress on the ground. And so if you're doing any drilling or whatever to try and put in additional piling, that will have an influence on the existing foundation system. So you must always be very careful in your corrective measures that you are aware of the risks and you take measures to mitigate those risks in the foundation correction.
So the next question here comes from Debanshu from IIT Dhanbad. His question is basically, if at a particular site there is soft soil strata and perhaps near a sea beach or any other similar kind of places, and we are constrained with a shallow foundation, what needs to be done for this sort of a challenging problem?
Well, I guess the standard solution to that, where you've got soft clays, is that it may not be feasible to use a shallow foundation if your settlement criteria and your bearing capacity criteria are not satisfied. I think in the design process, we usually start off seeing whether or not a shallow foundation can do the job for us. And if it can't do the job on the surface, we look to see whether by doing excavation and doing some form of compensation, by excavating and taking away part of the weight of the soil, whether that is a solution that we can use. If that doesn't work, then we need to go to a deeper foundation, whether it's a pier, whether it's a raft, or whether it's a more complete pile solution. That's just something that I guess we have to work out. But we always have a look at how far we can go with the most obvious and the most sustainable and cheap solution, which is generally a shallow foundation.
The next one comes from Usama from Arcadis, and he's basically interested to know your thoughts about possible or probable settlement values for highway bridge footings, which may have a design life of about 120 or 150 years.
Yeah, there you've got a real, I guess, problem with durability. One of the things that worries me is that we don't have 100 years of experience on durability. So I think that in terms of settlements, in most cases, within that period of time, the settlement will have occurred, and it is more likely that the deterioration of the structural properties of the foundation rather than of the geotechnical performance of the foundation may occur. Now, of course, the other possibility with long-term bridge foundations is that the loadings that may be applied to the bridge may have increased knowingly or unknowingly. And so we must always be aware that sometimes people that use the bridges don't always respect the loading limits.
What would your suggestion for bearing capacity and settlement calculation from shallow foundation on mixed soils, for example, containing a mixture of fine and clay, fine and coarse-grained soils? For bearing capacity, we may check drained and undrained conditions separately. How about settlement? For example, consider clay consolidation behavior. What do you think the percentage of plastic fines that will govern the behavior? Is it 20, 30, or 40%?
Yeah, look, that's a very good question. And one of the problems with what I've presented to you is that I've told you about sands and I've told you about clays. But in general, we don't have one or the other. We usually have a mixture. And this is why it's always useful, and part of my practice and what I try and get my colleagues to do is never to rely on one method of calculation. So if, for example, we've got SPTs, we've got CPTs, and then we've got consolidation data, I try and get them to use all methods to see what sort of values we get, because as the questioner rightly points out, almost inevitably we'll have some mixture of soils, and when does a sand become a sand and not something else? And I would say it's generally, and this is one of the attractions, I suppose, of methods such as CPT methods, is that it doesn't necessarily demand that we categorize the soil as a sand or a clay, because these days the cone test in particular will tend to categorize the soil itself and give us the necessary correlation. So I'm sorry, I can't be more specific than that, but never rely just on one method of settlement calculation.
The next question is around how should one address modulus of soils under sustained service loads versus transient, for example, earthquake or wind loadings?
Yeah, very good question. I think the situation, I mean, it depends really on what analysis tools you have. The situation is that you have, let's say, a constant long-term loading, okay? So the settlement under that load will depend on that loading and on the time that's gone. So you will have a final settlement. Now, if you have then, let's say, earthquake loading, that tends to be fairly rapidly applied and certainly a cyclic loading. So the movements due to that earthquake will tend to be undrained contributions to that baseline settlement that we've already got, so that you will have a long-term settlement, then you will have some perturbation of settlement during and after the earthquake is concerned. Now, the thing about that is that if you've had long-term consolidation, then the stiffness of the soil is likely to be much greater than it was initially. And so your movements due to that rapid loading will tend to be in the unload reload range rather than in the virgin compression range. So you need to try and understand the mechanics of the problem that you're dealing with. And if I was doing that and somebody asked me, okay, well, I've got a long-term settlement of 50 millimeters, but if I get an earthquake which causes certain increase in stress, what will the movement be? I would calculate that additional movement on the basis of the stiffness of the soil under unload reload conditions.
So the next question speaks to one of the formulations that Professor Mesri derived based on correlation for C alpha from natural moisture content. Yes. Can you comment on the efficacy of this method?
Look, when you've got nothing else, but a moisture content or a water content, you do have correlations then between your compression index, and your moisture content. And so that then gives you the CC value. And if you then want a first estimate of the C alpha value, then you would take 4 or 5% of that estimated value. I mean, you have to recognize that the more correlations you employ, the more likely it is that you will have inaccuracies in your estimate. But nevertheless, I mean, if that's all you've got, that's all you've got. And one of the, I guess, the values of experience is that you can sort of relate previous experiences to the current situation.
The next question asks about if you can perhaps provide some practical solutions if differential or excessive settlement is expected for a residential building due to compressible layer at upper 10 meters.
Yeah. Well, if you've got a compressible layer, I would say the easiest thing to do is really to use piers that go through that compressible layer. I know there, again, it depends. You can do smart engineering and you can, to a limited extent, perhaps remove some of the soil and replace it with the structure so that you have a partially floating foundation. But the simple solution is probably to use piers that go through that softer layer onto the stiffer bearing stratum. I know this is often expensive, but again, you have to recognize that the level of risk associated with that solution is probably less than the level of risk associated with trying to use a shallow foundation and risking differential settlements. About using shallow foundations is that, as I mentioned before, if you have individual footings and they're not tied together, the risks of having horizontal strains are much greater. And so the potential for damage of your building is much greater. So at the very least, if you're using a shallow foundation, use a raft or a series of like a waffle pod type of substructure.
To what extent the secondary consolidation could lead to the serviceability of the foundation, or maybe could impact the serviceability of the foundation?
Yeah, that's a good question. In general, we probably don't really see too much in the way of secondary compression. Part of the problem, again, is that our long-term settlement measurements are very limited. Where they've been done in situations where there's soft clays, for example, in Norway, where they've got the quick clays, and also on embankments where you've got very soft clays. And there, creep settlements can be quite significant. In normal building situations where you, particularly if you've got sands or stiffer clays, I would say that creep settlement secondary compression is not important. But I know certainly in some of the highway projects that we've been involved with in Australia, where you've got 20 or 30 meters of soft clay, the creep component of settlement can be significant. I mean, it can be half a meter or more over a period of time. So it again depends on the thickness of the layer, its compressibility, and also on the level of stress as compared with the bearing capacity. And that's the problem with embankments, that generally your factor of safety is 1.3 to 1.5. And so the level of nonlinear movements and creep is much greater in those cases. Thank you to all that have tuned in. I appreciate your resilience and your patience. Thank you.